hangisine yanayım? Yine tazelendi yürek yarası. Ben bu derde hamde derman bulayım. Meğer dost elimden ola çaresi. Efendim efendim benim efendim. Benim bu derdime derman efendim. Ben bu derde hande derman bulayım. Meğer dost elimden ola çaresi. Efendim efendim benim efendim. Benim bu derdime derman efendim.
Yeah. Oh, this thing.
Well. Let's go for it. All right. Hi, everyone. My name is Jessica, and I'm here on behalf of Delta Sigma Pi's Spring 2018 Pledge Class. So this upcoming Monday, we're hosting an event on machine learning. So I'm here to tell you all about it. We'll have a lot of cool speakers from Google, Amazon, Facebook, and we really encourage you to come out. We'll have a resume drop if you're looking for internships, and you'll have a chance to talk with all these industry leaders, and it'll be a really cool experience. In addition, we'll have free food afterwards, including sponsorships from Cream, Chipotle, McDonald's, Subway, and stuff like that. And then we also have a really fun raffle prize where we're raffling an iPhone X and AirPods. So again, this event is on machine learning. It's Monday at 6:30 in Anderson Auditorium in Haas. So I encourage everyone to come out. We have a Facebook event. It's called Machine Learning Workforce Up Tomorrow. RSVP, press going, and invite all your friends to come out. So thank you guys.
All right, thank you.
All right, thank you.
You got it. Cool. All right, these Turkish jams I'm playing quietly in the background. I was inspired by the rain. I was in Gurame, which is in central Turkey, a few years ago, and the weather was super miserable. But then we went to some cafe, and we had food that was delicious. And we had not had a lot of delicious food in Turkey because we're vegetarians. Yeah, it was a good day. And over the speakers, they were playing this guy who's a classical Turkish musician who's well known. Any Turks here? Oh, hey. Do you know about this guy? Wrong one. Let's see. Where's his name? Not that one. This guy. No. Hold on. Come on, Internet. I can't. We're just going to hold and wait so I can ask a Turk question. Okay, hold on a second. That's not the main guy I wanted. Anyway, Erkan Ogur. Maybe, don't know him. Okay, it's pretty obscure, I think. Just curious. All right, Project 3 is coming out imminently, but let's get going with today's content. So, as with last time, I'm going to kick it off with a graph problem. And what I'd like you to do, just to warm up, because we're going to be using similar ideas today, find me the shortest path tree for this graph, assuming S is the source. And then, if you have a little extra time to think, in what order is Dijkstra's algorithm going to visit the vertices? So try that out. Give you a little more time. Okay, I'm going to spoil it, even if you haven't finished it yet. The shortest path tree for this graph is as shown. And the order in which Dijkstra's algorithm will visit the vertices will be in order of their distance from the source. So, for example, vertex 4, its total distance from the source is what? 5. Okay, so it's going to happen fairly early. In fact, it'll be earlier than this vertex, which is total distance 6, and this one, which is total distance 7. All right, any questions about that? Just we'll be doing something kind of related today. Okay, I got another one for you. Now give me a topological sort or topological ordering, either way you want to call it, for the graph below. And if you want the same answer as me, you should use that whole algorithm we had from before. So I'll give you guys a minute or so to do this. And it'll all relate to today's content eventually. If you don't quite remember what that means, think of the arrows as tasks that need to get done, and you have to do the prerequisites before you can do the later ones. So hint, 0 is a good starting point. And there are multiple correct answers. Okay, I'm going to give you one. So one possible answer is 0, 3, 1, 2, 4, 5. So in this case, the topological sort, it is 0, 1, 3, 4, 5, 2. It is different. Okay. So in this case, the ordering is not based on your distance from the source, but on an ordering that satisfies the arrows. And there are other possible orderings. But as a reminder, yes. Is it the only one? Maybe it is the only one, actually. Yeah, probably it is. Okay, yes. So the topological ordering of this graph that I came up with, probably also the only one, is 0, 3, 1, 2, 4, 5. And as we see, whenever we have come up with an ordering, we can do this cute little thing where we reorder the vertices and we, what is sometimes called linearization, where we take the graph and we put it on a line, and you see all the arrows point to the right. Okay? Now this is going to be really important for today, and isn't it lovely? Okay, so some refreshers. All right, so moving on, we're going to be talking about something known as dynamic programming today. It's sort of a funny term. It's a little nebulous, but it's an important problem-solving technique that's really more of a 170 thing, but I think it dovetails nicely with what we've just been doing in 61B, so I'll introduce it here so that it at least feels a little familiar when you do it for real in 170. But I think it's a nice application of graphs, and there's some cute stuff here. And I can introduce a couple of ideas that I really like. Okay, so the first thing I want to bring up is that there are some graphs which are acyclic, as you know, and some of which are directed, and graphs which are both are sometimes given the affectionate name DAG for directed acyclic graph. And these are a really, really important class of graphs that are used for modeling all sorts of things, and they also have a number of really nice mathematical properties. One of them is that any DAG can be topologically sorted. So if you don't have any cycles, then there is definitely some way to obey all of the constraints, and that, by the way, as I mentioned earlier, is sometimes called linearization. So given any DAG, you can linearize it. You can make it into a nice line. You can topologically sort it. And there's another nice property, which is that it is very easy to find shortest paths conceptually and runtime-wise on a DAG. So one approach to finding the shortest paths tree in a DAG would be use Dijkstra's algorithm, which is maybe what you did, or maybe you did something more intuitive. But it turns out that if you have a DAG, and only if you have a DAG, it is safe to, instead of relaxing edges in order of their distance from the source, you can instead relax you can visit the vertices in their topological ordering. Okay? So that's nice, because that saves you having to build a priority queue and tracking all these distances. You just need to know what order to do the vertices in. So this is an example of an alternate shortest paths tree algorithm, and this one only works for DAGs. Okay? So how it works is we're going to visit our vertices in topological order. I don't like this thing. So I learned a cool trick recently where you can do inspect, and you're like, I don't like this bar that keeps popping up. It's terrible. So I'm going to, let's see, where is it? Okay. Oh, it's hard to do on my laptop. I wanted to do the trick. Okay. Go away, bar. And come back. Okay. And I want to delete it, but I can't find it. Maybe it's this one. Oh, there it is. Okay. Now I'm going to say delete element. All right. Now it's gone, hopefully. All right. Yeah. See, it's gone. All right. So my goal... Hey, my goal is to figure out how to write a Tamper Monkey plugin to make that go away forever, so I don't have that thing showing up. I was so relieved to discover this. Anyway, alrighty, so we've deleted that bad thing, and now we can proceed with our example. So what I'm going to do is just the same old process like we did with Dijkstra's, only now I'm going to be going in the order of the vertices on the page instead of thinking about their shortest paths distance from the source. Okay, so first I relax 2 and 2. So these are better than infinity, clearly, so I'm going to replace them with 2. Great. All right, now we go on to vertex 3. At this point, there are two different ways that I could potentially get to vertex 1 from the source. There's the original one I already had, and there's this new one. What's the new path length? 6. This is shortest paths, not spanning trees. So the total is 6. 6. And so 6 is worse than 2, so we're not going to use it. How about this? What's this going to turn into? 5. Okay, so that's all. So we change that. Okay, we move on. Now we could just use the next vertex. And again, we aren't really paying attention to the order of the distance from the source. We're just going in linear order. Okay, so next up, this is going to become 8. Okay, this is going to become... not going to change. It stays as 5, and this one is 9. Okay, now we get to this one. 6. All right, good. That's it. So this is an alternate shortest paths tree algorithm that only works for DAGs. It's a nice it's a nice algorithm. And I'll talk a little tiny bit about why it works. Okay, so any questions about this algorithm? It's literally just like Dijkstra's, except that you just go in the order that it appears on the page. All right. So it's different than Dijkstra's because with Dijkstra's we actually had a priority queue that tracked distance from the source, but here you don't need to because the graph is specifically a directed acyclic graph. Okay? So the runtime of this algorithm is just E plus V. The first step is you have to topologically sort your graph. See, it's back because I opened a new window, but we'll live with it now. Okay. Your days are numbered though thing. Anyway, so you have to do a topological sort, which is theta E plus V time. Then you need to initialize an array of size V, actually a couple of them, distance 2 and edge 2. And then you need to finally go through and relax every edge exactly once, and that's going to be theta E time. So the overall runtime will just be theta E plus V. So it's faster than Dijkstra's algorithm, which had a log factor because we had to track an ordering of the vertices. But here there's no need to track an ordering that changes over time. Okay. So this algorithm is an example of what's known as dynamic programming. Okay. Now I'm going to talk about it in a very broad way, and it takes actually a lot of practice to understand what exactly a dynamic programming problem is and what's not. I don't know that I 100% can answer for sure in all cases. There's some fuzzy cases, like people argue, is Dijkstra's an example of dynamic programming? I think the answer is no, but it's sort of a debatable thing. But we're not going to get to that level of sophistication, just a word of warning, okay? But basically, dynamic programming is any time you have really big subproblems, and then you want to solve it in terms of smaller subproblems, which you'll typically actually, I think you should always memorize the answer to those smaller subproblems, and that makes the bigger subproblems easier to solve, okay? So the DAG shortest paths tree algorithm, you could think of it as solving increasingly large subproblems. And this is a pseudo-proof of why it works. So the distance from the source to the source, I hope you agree, is very easy. It's just 0. And then we're going to tackle distances that are just a bit further over to the right. And because of the structure of the graph, as soon as I handle all the things that are right next to the source, and once those have all been processed, there's no way that there's ever going to be a shorter path that we missed, just naively moving forwards in topological order. And we just repeat that process over and over until we get to the end of the graph. And so instead of having to recompute all the shortest path stuff over and over, the fact that you've done the early close to the source ones already means that you save yourself some work. So in some sense, we say that the problems grow larger and larger. It is harder to compute the distance to the very end of the graph, but it's not so hard if you've already done all the ones before it. Okay? And so when I say the problems are larger than others, I mean they depend on more and more of the earlier subproblems. Okay? So that's all really dynamic programming means. But I think just, it's a weird name, right? It feels like it should mean something more. And so dynamic programming is, I think most people, including the inventor of the term, would agree it's a terrible name for what's basically a simple and powerful idea for solving complex problems, which is identify a collection of subproblems, solve the subproblems one by one, going from the little ones to the big ones, and use the answers to the smaller problems, which you memorize, to solve the larger ones. And what you'll find when you take 170 especially, is that you'll get a chance to try and, given a big problem, figure out what the little problems are, and that's a hard problem that's a bit of an art. And we're only going to see one really interesting example in today's lecture, and so I'm going to defer really the deep part of dynamic programming to 170. But I do want to actually talk a little bit about this name dynamic programming. So there's a cute story about how it came to be. It's a well-known thing from a book, but Quora, this book isn't online, so I just had to go to this Quora post. So Bellman, who's a very famous algorithms guy from way back, he invented a bunch of algorithms like the Bellman-Ford algorithm, which is an algorithm for finding shortest paths, even if you have negative edges. He writes about the time he had. in 1950. So he was at Rand Corporation, which does all kinds of things, think tanking and math in this case. And he said his task at Rand was to find a name for what he called multi-stage decision processes. Well, that sounds like a name already, but okay. Anyway, so where did the name dynamic programming come from, which is what he ultimately ended up using? Well, he says the 1950s were not good years for math research. There was a guy in Washington named Wilson who was Secretary of Defense, and he had a pathological fear and hatred of the word research. I'm not using the term lightly. I'm using it precisely. His face would suffuse, he would turn red, and he would get violent if people used the term research in his presence. You can imagine how he felt then about the term mathematical. So he goes on to say that the Rand Corporation worked for the Air Force, and the Air Force had Wilson, who was the Secretary of Defense, as its boss. And so he had to shield Wilson and the Air Force from the fact that he was doing math inside the Rand Corporation. Otherwise, he wouldn't get grant funding. So what name could he choose? Well, he was interested in planning, but he didn't think planning was a good word for various reasons, so he decided to use the word programming. So when he says programming, it's not programming like you and I use it in the year 2018, but it was 1950s word programming, meaning something maybe a little more like television or radio programming, like planning. So it's not writing code. He also wanted to get across the idea that this was dynamic. It was multi-stage. You solve the little problems, then the big ones. And he decided, okay, well, let's kill two birds with one stone. Let's take a word that has an absolutely precise meaning like dynamic. And it also, he liked the word dynamic because it is impossible to use in a pejorative sense. You can't say like, oh, that guy's so dynamic, and then it sounds bad. So dynamic, it just sounds nice. There's no way to make it sound bad. And so he said, try thinking of some combination of the word dynamic with something else that sounds negative. It's impossible. So I thought dynamic programming was a good name. It was something not even a congressman could object to. So I used it as an umbrella for my activities. Okay. So whenever you in 2018 are thinking, is dynamic programming something like functional programming, like a new paradigm? No. It is this process. Okay, so just be warned, programming does not mean programming as you know it. Okay, it meant something like planning. All right, good. And that's actually a good political lesson that may be useful to you in the future. Okay. So now let's talk about one of the most classic examples of a problem that's solvable using dynamic programming called longest increasing subsequence. And we're going to start by doing it in a little bit of a funny way. Okay. So our goal is given, this is going to be the main thrust of the whole lecture from now on, given a sequence of numbers, find the longest increasing subsequence, where a subsequence is some subset of the numbers from before in the same ordering. So for example, if I have 6, 2, 8, 4, 5, 7, the longest increasing subsequence of that is 2, 4, 5, 7. So those numbers all appear in the original sequence, and these appear in the same order, and they're all increasing. There's a related problem, which is trivially related, which is find the length of the longest increasing subsequence. And here, since the longest increasing subsequence is 2, 4, 5, 7, the length of this is 4. So let's make sure that problem makes sense. Just a quick little one for you to do on your own with your own eyeballs. If we have 5, 2, 8, 6, 3, 6, 9, 7, what's the answer? I'll wait just a little longer, because you got to understand what the problem is, otherwise the day will be sad. Okay, so answer is 2, 3, 6, 9, and the length of the longest sequence is 4. Now I didn't give you any algorithm for doing that, and that's what we're going to be developing. Anybody unhappy with it? All right. So the reason it's 2, 3, 6, 9 and not 3, 6, 9 is because this one is longer and increasing, but they're both subsequences. Yeah. Say again? What's wrong with D? It's not a subsequence. So in this case, you can't just reuse certain numbers multiple times. And you can't reorder them. It has to appear in the same order as the original sequence. Yeah. All right, good. Yeah. 2, 3, 6, 7. That also works. Yep. So that would be a valid answer as well. So there are multiple answers. All right, so if you pick something else, that's valid too. All right. So how do we do this? Well, there are a bunch of different ways to do it. We'll start with a way that's kind of interesting. So there's a fun notion in computer science, which is we have all these different mathematical tools, and sometimes you can take a problem and like bend it to fit another problem you already have an algorithm to solve. And we did that a little bit, like with priority queues. We used priority queues to solve word puzzles and board puzzles and so forth. So we're going to do something a little similar here. Okay. So the first thing I'm going to do is I'm going to point out a connection between the longest increasing subsequence problem and directed acyclic graphs, right? So given a sequence like 8294573, a little longer, the longest increasing subsequence of this is 2457, and the length of the longest increasing sequence is 4. So I'm going to make an observation that will be helpful for us visualizing what's going on, which is we could draw a directed acyclic graph where we just put one vertex per number, and I add an arrow from one number to another if that first number appears earlier in the sequence, and what else? What's the other property you kind of infer? I'm dropping on it here. If it's increasing, yeah, if the left number is smaller than the right one. So this captures all of the less than relationships, and so now using this, you can maybe imagine trying to solve the problem. Okay? So what I'd like you to do real quick, this is just an open-ended problem. In terms of this directed acyclic graph, what is the length of the longest increasing subsequence problem? So what property of this DAG are you looking for? Is it the shortest path? Is it the number of edges? Is it, I don't know, the reverse post order? What is it? What is the length of the longest increasing subsequence? You don't have to figure out how to solve it. Just figure out what property of the DAG do we want. Okay, any thoughts? Yeah. Sure, you go. Highest degree of the node. Okay, I don't think it's actually degree related. Yeah. Find the longest path that appears in the graph. Yep, that's what I had in mind. So it's the length of the longest path, but it's not just that. It's the length of the longest path plus 1. Why is it off by 1? Because the path has two numbers on either end, right? So 2, 4, 5, 7, it has 3 arrows between it. Okay? So that's our goal, yeah. So, I mean, it is the topological sort of some particular graph. In this case, I didn't actually have to compute the topological sort of anything. I just created a graph where 8 appeared first, then 2, then 9, then 4, then 5, then 7, 3. No, yeah, topological sort has nothing to do with the length of the path or anything. So, I don't know if topological sort is useful to us yet. Yeah. So how fast is it to build the DAG? It's not so bad. In the worst case, it would just be n squared. Yeah. I think it's just n squared. Alright. Okay, harder problem for you. Give me an algorithm for finding the length of the longest path in a DAG. So I'll let you think about this one for a little bit. This is a real hard problem. Doesn't sound hard, but it is hard. I'll give you a hint in 15 seconds. Okay, my hint is that the DAG shortest paths tree algorithm works even if you have negative weight edges. All right. So here's one possible answer, which is give every edge weight -1, and then for every vertex, run the DAG shortest paths tree algorithm. That's the one we used that only worked for DAGs, where we just relax in topological order. And what we'll do is keep track of the length of the longest path starting at some particular vertex in some array or list or whatever, and then we'll return the max of that. Okay? So let me show you by example. I think it'll be a little more clear. Okay. So what we'll do is I run the DAG shortest path tree algorithm starting at 8. When we run this algorithm, we relax all the vertices in order, but we go through the vertices in order, but if we only consider what's reachable from 8, so there's a little extra work, but not much, we'll find that the longest path, if we start from 8, is -1. Okay? How about if we go from 2? Well, in that case, we're going to compute the distance of all things reachable from 2, and so we'll end up, in this case, the shortest path will be -3. Okay? Because remember how relaxation works. It says, is the number I'm computing less than? If so, accept it. And so in this case, I'll get a shortest path of -3. So I'll take that -3. So out of all these distances, these are all the distances that are computed, I will find the minimum, which is -3. I'll take the absolute value, because I actually care about the length. And so the longest path in that case is 3. We then repeat for 9. So if we go from 9, what's the longest path? Oh, this should say 0. That's what I get for copying and pasting. Okay. You guys are guinea pigs, because I changed up how this lecture's done, so see how it goes. Anyway, so this is the distance of the longest path from 9. There's not much you can do. From 4, there's 3 reachable vertices, and the shortest path is of length -2. So we'll take the minimum from all of these distance values, and then do the absolute value, and so forth. All right. Questions about this? We're not done yet, but yeah. You could get away with not creating this graph, but I'm just doing it as a crude way. Another answer, I'm going to forestall or predict a question someone might have, which is, can't we just do DAG shortest paths where we reverse the notion of relax? That also works, but then we have to explain that. So I think this also is easier to understand, for me at least. Yeah. Yeah, it feels weird to do 4 when you already did 2. So we'll be improving on that. So there's some redundancy here. Yeah. Either one. Someone's got to step up, though. I'm running it from every vertex. So I did it from 8, then 2, then 9, then 4. I'm not done yet. So I'll do it from 5, and I get another. What's the longest path from 5? The length of the longest path. 1. Okay, so that's why I'm putting 1 here. Okay, the length of the longest path starting at 7, 0. At 3, also 0. So in other words, if I ran this algorithm over and over from every single one of these vertices, the one that had the longest path was when I started from 2. There's that 3 that showed up. And so the final step of the algorithm is just take your big ol' array. We gotta wait for that dumb thing to go away that I don't want to delete again. And so we'll just find the max of that array of absolute value of minimums, and we get 3. Right, so this is the kind of backbending you'll see a lot in 170, where you take a problem and then you bend it in a funny way where you're like, assign all the weights to be -1 and then just run it through another algorithm. And this is a slightly cleaner approach than changing the algorithm itself, because the alternate approach would be change the DAG shortest path tree algorithm so that it considers relaxation in the opposite order. This just ends up being, I guess, a little more par for the course for what we see in 170 type courses. Yes. You might have been, I don't see no 6s here. There might have been an old 6. See, 8, 2, 9, 4, 5, 7. Oh, geez. You know, okay. Sorry. Yeah, you guys are my guinea pigs, as I said. Don't worry, I'll fix them later. I think the intention is clear, I hope. So this should always say 8, then 2, then 9. Okay, sorry. Thank you. So some of those might be a little messy. I apologize. I changed it before class, and like today I ended up having many meetings I did not anticipate. So thank you for catching that. Yes? The purpose of setting the weights to -1 is because the DAG shortest paths tree algorithm will find the shortest path. So, for example, from here, the shortest path has distance -3, right? If we'd done DAG shortest path with positive weights, it wouldn't find this as the distance. It would say these are actually worse. So if you try running with positive weights, you don't get what you want. Alright, so it's a cute trick. But as you can see, there's a little bit of redundancy and maybe a little, some 6s that appeared occasionally. Thank you. Alright, so the runtime of this algorithm, with all of its redundancy, hopefully you agree with me that it's correct, that it will give you the right answer, but the runtime is a little silly. It's big O of n cubed. I mean, it's not so bad, but we can do better. And the main strange thing is that it feels bad to be running the algorithm from 4 when we already did 2. So we'll fix that in a bit. So to summarize what we did, given a sequence of integers, we transformed our problem into a problem on directed acyclic graphs, and that process is sometimes called reduction. And when you look at all the really classic 1970s work on like NP completeness and all these, reduction is one of the most important tools. And it's something that's used on a practical basis quite often, where I have an algorithm. Someone already wrote the code that solves whatever thing. I mean, sometimes it's something very mathematical, like DAG shortest paths. And I just take my problem, which maybe has to do with, I don't know, baseball, and then I cast it as a graph problem, I run it through the algorithm, and now I get the answer I want. Okay? And so ultimately what we did is we reduced this problem of finding the length of the longest increasing subsequence to n solutions of the longest paths problem. Okay? And so in theory and in practice, but especially in theory, this kind of thing is very common. And so the way we solved this longest path problem on DAGs was by running this dynamic programming algorithm called DAG shortest path tree. So that's kind of the flow we did. Now we'll clean it up a little. That's our initial approach. Okay? And this approach is a general thing that you'll see a lot, especially if you take theory classes. Okay? So now let's talk about an approach which uses dynamic programming a little more aggressively. So technically here we were using dynamic programming because DAG shortest path tree was an example, but we're going to get even smarter. Okay, we're going to pick smarter subproblems, and that's going to mean we can eventually just not have a graph at all, as we'll get there. Okay? So the process that we described earlier, this is just a repeat of everything we've been saying. The process we described earlier, it felt a little redundant. We shouldn't be finding the DAG shortest paths tree, when I'm trying to find the DAG shortest paths tree for s equals 2, that is actually a subproblem, if you think about it a certain way, for s equals 4. So if you've already done, is that backwards? But we ran both in their entirety. Which one feels like a subproblem of which? Yeah, okay. The direction we were going, yes. But the way we're going to go, it's going to be the other way. Thank you. So there's many ways to fix this issue of being a little redundant. But we're going to use dynamic programming directly as a way to do it today. Okay? So again, dynamic programming, whenever you're doing it, the whole goal is to identify a collection of subproblems to save you some work. And then we solve the subproblems one by one, going from small to large, and we're going to use the memoized small problems to help solve the large ones. Okay. So I'm going to turn everything over a little bit. If you already were like, oh god, we did negative ones. Okay, well don't worry, I got another weird twist for you. Alright? So the subproblem I'm going to pick is not what is the length of the longest subsequence starting at a particular vertex, but rather what's the length of the longest subsequence ending at a particular vertex. So for example, if we just look at 8, 2, and 9, we ask ourselves, what is the length of the longest subproblem ending at index number 2? Okay? Well, it's 2. Either you can go from 2 to 9 or 8 to 9. But the length of the longest problem ending at vertex number 2 is just 2. Okay? And it turns out that this, if we think about trying to find the answer to ending at, we're going to be able to avoid a lot of redundancy, as we'll see soon. Okay. So let me give you some more examples. So given this whole sequence here, if I ask for the length of the longest sequence that ends at 2, at index 2. So this is not like the number 2. It's it's value 9 because it's 0, 1, 2. That's 2. Let's define Q of K. So this is going to be our memoization array, basically. So Q of K is going to be the length of the longest increasing subsequence ending at K. So in other words, this LLSEA problem. It's another problem. It's our subproblem for LLIS. And so we can say, if we're talking about ending at vertex 1, or at number 1, the length of the longest path, if we end at 2, at the value 2, is just 1. Like you just start there. You can't increase. If we go up to the third item in my array, okay, I'm going to give you a chance to do it in a moment, but if K is equal to 3, if we're going up to the third item in my array, in this case it's 2, right, going from 2 to 4. Okay? And so these Q values, they're solutions to our subproblem, the length of the longest sequence ending at a problem. So when I said in 170 you talk about identifying the right subproblem and it's hard, probably for you it's not totally clear why all of a sudden I've switched to ending at, but doing this, that's the tricky part of this dynamic programming problem. And once I decided that this is what I care about, things will all roll off the tip of our tongues. Now let me just give you a chance to relax and think about what's going on before I go any further. I'd like you to tell me, what is Q of 5? Remember that Q of 5, it's the solution to the length of the longest subsequence ending at 5. And so I'll give you guys a minute and a half Just so you can either talk to each other and just figure out what's been going on too, just in case you got a little bit lost. Was it the same? Oh no. Alright. That's sad. Wonder what happened. Okay. Well, don't answer it online then. Yeah, I just opened it and was confused myself. Okay. So, the length of the longest sequence that ends at the number 7, k equals 5, is 4. Here it is. 2, 4, 5, 7. It's our old friend. Okay? Any questions about what we're doing? Or about this? Yes. Are you going to recompute at every vertex? Well, we haven't talked about an algorithm. I just wanted you to do it however you want. The magic of being more efficient hasn't happened yet. Yeah. Yeah, so this approach is going to better leverage memoization. And here's something for you to think about. Okay, this YAL key should be correct. All right. So here's a really nice fact. The reason I've introduced LLSEA out of nowhere is that if you do so, you can use the results for small q to compute the results for large q. So let's suppose that we know for a much longer sequence, we know q of 0 through 103. We've already solved all our subproblems, and now we want q of 104. Here's my graph. And let's assume that all the values that are not shown on the page, there's actually 105 things here. Assuming that all the ones off the screen are all small. And so your goal is to figure out what is q of 104, given what's here. This is the more interesting question, I think. 20 more seconds. Okay, so question for you guys. What's the length of the longest increasing subsequence that ends at this number 330? 61. So there's some sequence of digits going up to this one that's 61 digits long. If we added 417 to that, would that also be a valid increasing subsequence? Yeah, because it's bigger. There's an arrow, right? So how long would that one be? 62. Okay, how about this one? What's the length of the longest increasing subsequence ending at 573? 77. If we add 417 to the end, would that be valid? No, so we can't use that one. We can use this one, and we can use this one. But so all three of these sequences can be made one longer by just adding 417. And so we compare 62, 49, and 45, and 62 is the biggest. Okay? So this is the way to think about it. Of all the increasing subsequences that have an edge pointing at 104, the longest one was at length 61. Okay? And it was the one that ended at node 100. Okay? So you can think of these Q values as the memoized answers to all these shorter problems. And so I just said this out loud, but we've memoized the answers to all the earlier ones. And so this one, well, if we want to know the length of the longest increasing subsequence ending at this node, we can use these. Oh, okay, sorry. K is 104, and I'll say Q. Actually, I'll add it to this part. It was correct. It just didn't have the number you guys wanted to see. Okay. All right, any questions about that? All right. Yeah. Why? There might be some reason. Okay, so maybe this number is weird, but all right. It's not important. It's a good question. Is this number possible? Maybe not. All right. All right, here's a nice fact. We can use our Q values to solve the length of the longest increasing subsequence for the entire sequence. So remember that Q of K is the length of the longest subsequence that ends at K. And so if we just take the max over all of our LLSEA solutions, that will be the solution to the entire problem. So in other words, if I want to know the length of the longest subsequence, I could say, what's the length of the longest sequence ending at A, ending at the number 8, ending at the number 2, the number 9, the number 4, and so forth. So out of these choices, I have 1, 1, 2, 2, 3, 4, and 2. Which one do you think is best? 4, okay? So that's how I could do it. So if I compute all of the Q values, I get an array, and I just take the max of that, and that's my answer. Okay? So that's the algorithm I got. So in essence, the algorithm we've come up with is as follows. Okay, we're going to optimize one more time, but what we're going to do is we create Q, which is an array of length n. We set Q of 0 equal to 1. We set Q of K equal to negative infinity for all the rest. We then create a directed acyclic graph with n vertices, and we draw an edge between them if the left vertex is less than the right one. And then for each K, we have to solve the length of the longest sequence ending at K. We consider for every L up to it, if there exists an edge from L to K, that means it's a valid thing to accept. Then we're going to say, if it's bigger than the best known, set it equal. So that's just basically the process we did here. We look at all the things to the left, and if it has an arrow pointing at us, then we will add 1 to whatever numbers were there. That's it. And so the runtime here is creating the array, and the directed acyclic graph are going to be theta n and theta n squared, respectively, where n is the number of numbers. And then the runtime of this loop is also just a for loop. That's, you can show that this is, well, if you think about this, it's two nested for loops. This one goes up to n, this one goes up to k, where k goes up to n. So this will overall be theta n squared. Okay? Now it turns out that the graph isn't actually necessary. What do we use the graph for? We used it to decide if this is valid. Like, if there's an edge, then it's useful. If it's not there, if there's no edge, then it's not valid. So that's that. So we can actually just get rid of the graph entirely, which is why this isn't really a graphs lecture. And we could just say, okay, instead of asking the graph, is there an edge? You can just say if item L is less than item K. It's tantamount, right? And so in that case, it's the same exact runtime, it's just we don't need a graph now. Okay? So it's the DAG-less version of this dynamic programming. Nonetheless, even though you don't need to explicitly build the graph, I think having the graph in your mind helps understand the algorithm, but once you're an expert, you don't need it. So to summarize these different runtimes here, approach 1, we had this sort of janky approach where we said, okay, I just want to use the minimum possible mental effort, or like I don't want to deal with any kind of algorithm machinery. But I do have one thing. I have a hammer which knows how to find the shortest paths on graphs, even if they have negative weights, as long as they're directed acyclic graphs. So I'm going to take my sequence. I'm going to build this graph. This is the original algorithm. I'm going to run DAG shortest paths tree n times, compute these numbers, which was the length, the number of items along those paths. We'll take the max and add 1. That was our original approach, and it was theta n cubed, which we didn't prove, but it's in the extra slides, which maybe we have time to do. Approach 2, which we did, which was a little better, is we took our sequence, we built the graph, then we did this memoized problem. And the main punchline here was that we could use memoization if, and only if, we decided to look at the length of the longest subsequence ending at a particular number. And that's what Q represents. They gave us a different array, which we compute the max of when we get 4. And then finally we had the DAG-less version of this, where we just have a bunch of Q values, and we don't need a graph. We could just compare the numbers literally, and that's that. Okay. So any questions about all of this? So this is an example of dynamic programming. Yeah. So you can look at the longest path starting and look at the end of the array. What do you mean? Sorry, say again. So longest paths, okay, so you start from the end of the array and work your way to the front with longest paths. Is that the right idea? Maybe. My only concern with longest paths, so it turns out that finding the longest path in an array is an NP-complete problem. It seems like it shouldn't be hard, and we'll learn what NP-complete means at the very end of the semester, but there's no known algorithm for a general graph. I mean, for a DAG it's different, as we've seen. Okay, yeah, no, since it's a DAG though, I think that's appropriate. So you could do it the other way around, with longest paths working the other way. That seems likely. Other thoughts? Okay. Now that we're in the awkward position where we don't have quite enough time to do this, but we're also done a little early. Because as I said, today was a little bit of an experimental lecture. It's a newish topic that I decided to apparently make more efficient. Because I think we got through that and it made sense. So I don't know. Maybe I'll just field some random questions about anything while we're here. Why not? What do you got? And we'll go soon. Or we can just call it a day. Anybody got any questions about anything at all? Yeah. So who would I take on a deserted island if I couldn't be rescued? That's such an easy one when you're 36. I just bring like my wife or maybe my baby, but probably my wife, because you guys can take care of the baby. Yeah. My baby's cool, but I don't want to consign her to a life on a desert island. But I think we'd be cool chilling out. Play what? Fortnite. I actually don't know what Fortnite is, but sorry. Yeah. What data structure am I? I don't know. I'm a random assembly of molecules. I couldn't really say. Yeah, back in the back. Oh, it wasn't what data structure. It said what should we name the baby? But we didn't use any of them. Yeah. Yeah. But we read all of them. It's fun. Way in the back. Yeah. What's it again? When will I what? Oh, bring the baby? I'll probably bring her the last day. Yeah. Yeah. Sure. I mean, it's been in it before. I thought it'd be kind of fun. I just think it's nice to see. Here's my baby eating some bread this morning at daycare. Okay, I'll just leave this up. Yeah. My highest rank in StarCraft, I think I just got the platinum something. It was a while ago. I was actually fairly good, yeah. This weekend I'm going to work on making sure Project 3 is not broken in any way at all. Yeah, because there's some changes that are new, yeah. Yeah. Oh, when I ran for, I only ran for student government in 2008 so I could be in the newspapers. That's all I did. Yeah, I thought it would be fun. Yeah, I'll cycle to the front soon, yeah. What CS class should you take next semester? I don't know, there's a lot of, I mean, you're still pretty early. I would say like 70, 61C and all those. Those are good choices. I'm probably teaching Data 100, and I hope so. We'll see. Yeah. Runtime of my life? I mean, what's the variable? Like, what is N? How efficient I am. I mean, I don't even know what asymptotic runtime means in this context. All right, what's going on loop? Yeah. I'll come back. No, the snowman is still in existence. If you go to my old apartment, which was 1817 Woolsey, in the basement, wrapped around a pipe in the basement, is the original snowman outfit, so you don't hit your head. Yeah. I'm really excited about data science. I think it's cool. I want to know more about this other paradigm. I was just talking to Alyosha today about how these kids these days, when they learn to program, they go watch YouTube tutorials on TensorFlow, and then they don't learn to program the way we learn. So I want to know what that's like. Yeah. Oh, how many ASAG messages are there? I have no clue. There's some way to add them too. I don't know if you guys can, but there's a lot. Yeah. I don't do the squirrels or Oskies type question. All right, next. There's no good answer. Sorry. Yeah. How would I teach 62NA? The first time I taught it, I'd probably do it exactly like John, including all the saying announcements a certain way. And then after I taught it once, I would probably decide to change things in some way. But I feel like that class is so well crafted, I wouldn't want to change a lot. Though, I am thinking, John and I are talking about making some kind of follow-up or maybe alternative to 61A and B that's purely functional. It's called 61X. Maybe it'll be a systems class. Maybe it'll just be something, I don't know. Anyway, we're talking about it. Yeah. How did I meet my wife? So my research advisor was out of town for a conference. No, he's out of town for all kinds of stuff. So I had a month off from meetings. So I was like, I'm going to go to New York City or London for a month. And I did New York because it was easier. Then on the third day I was there, I was just meeting friends of friends because I said, who do you know in New York? And so we met on a Thursday and then we hung out every day for that month. The end. Yeah. That was in 2007 or 8 or something. Yeah. Dating advice for CS majors. I mean, the main thing, I don't think it's any different than anybody else. I think you just gotta go meet people and like do stuff and take advantage of the limited time you have to like do non-school work, I guess. But go out there and do stuff. That's my main thing. Always do the thing. When you have to decide between staying in and not doing the thing and doing the thing, do the thing unless you have homework to do. Which is always, yeah. TV shows are my favorite. Oh, that's interesting. Well, lately, so my wife is now going to be writing about Westworld for Wired. So no spoilers because we have a lot of catching up to do. But I'm enjoying it. I'm not really into violent things, but since they're robots, it feels kind of okay. But I don't know. Anyway, yeah. What's really good though? Like, what's transcendently good? There was this. I'm not really a huge fan of like weird cartoon thing. Like, what's that? Popular Rick and Morty. I've never seen Rick and Morty, but there was this thing involving. Oh God, what was it called? Something Xavier Renegade Angel or something. It's really weird from like 12 years ago. I thought that was sort of transcendently good. But yeah, I like absurd things, but also like things that are human and like have emotion to them. So, yeah. Friends of friends, depth first search or breadth first search? Definitely breadth first search, otherwise you've immediately moved to friends of friends of friends. It's not the right algorithm to meet them. Yeah, otherwise, yeah. Programming language, I mean, I don't know them well enough, but I love OCaml. I love the ML languages. They just feel good. Like, it feels like you're doing something correct and virtuous, yeah. I actually really like Java, weirdly, yeah. No, I don't think I could. I'm not good at impersonations. I can't really do, I mean, I could say announce. Both John and I kind of have weird voices a little bit. I don't know, so. I think we should just do our own separate voices, sorry. I'll practice, though, and maybe do it later. Any others? This went better than I thought. I thought you guys would try and get out of here real quick. Yeah. Skateboarding. I started when I was 24. I was a Berkeley grad student, and I saw this guy just blasting down a hill, and I was like, that looks awesome. Because I'd started surfing, and then I fell down a lot. I bought my first skateboard from a girl on Craigslist who was like, do you know what you're doing? And she was selling it because she'd gotten hurt and was done. And she's like, do you know what you're doing? I was like, nope. And then I fell a lot. But I eventually got good enough that I could just like go down the hill max speed all the way to BART from anywhere, and that was fun. Anyway. Yeah, one last question. Yeah, I did teach the class at Hillfinger in 2014, and I loved it. It was great. Fall 2014. You can go check it out. We have different philosophies about projects, but I love the man. Paul Hillfinger's a good guy. Go to his office hours. All right. See you guys. Hope you had fun. Hope you didn't waste your time. Always finish early.